So picture this. You are driving down the highway. You're doing like 70 miles an hour.
Right.
The radio is playing, the air conditioning is blasting to fight off the summer heat, and you're just completely relaxed. But right beneath the floorboards of your car, there are these heavily shielded industrial-grade cables pulsing with hundreds of volts of direct current.
Yeah, a massive amount of energy.
Exactly. We are talking about enough electrical energy to power an entire small neighborhood, just transferring instantaneously from a lithium-ion battery pack straight into dual electric motors.
It's a highly controlled, incredibly high-speed flow of immense power.
Right, it's controlled. But what happens if, just one of those high-voltage cables vibrates even a single millimeter out of place?
Well, the consequences are immediate.
Yeah.
And frankly, they are catastrophic. You're essentially looking at 3 distinct nightmare scenarios right off the bat.
Okay, lay them out for me.
First, you have the immediate risk of high-voltage electric shock. The chassis of the car itself could become energized, which endangers you, your passengers, or any first responders trying to approach the vehicle.
Oh, wow. Yeah, that's terrifying.
Second is the potential for electrical arcing. When high voltage jumps across a physical gap, it creates plasma. That plasma can instantly ignite the surrounding plastics and battery materials into an uncontrollable thermal runaway fire.
And battery fires are notoriously hard to put out.
Nearly impossible.
Yeah.
And the third scenario, even if a fire somehow doesn't start, a severed high-voltage connection means a sudden, total loss of motive power. You lose all braking torque from the motors while you are actively navigating highway traffic.
Which is just a complete nightmare. And that exact nightmare is the sole focus of today's deep dive. We are looking at a masterclass in how engineers prevent that from ever becoming a reality.
We really are.
Yeah, we are tearing into a highly specific, very dense technical source document today. It's a functional safety and fault diagnosis specification for hybrid dual motor power control systems.
Right, the PCS.
And we're focusing squarely on preventing a massive system failure known as the C01 HVIL open fault.
Yeah, so HVIL, for those who don't know, is an acronym. It stands for High Voltage Interlock Loop. And to really comprehend the scale of the engineering we're about to discuss, you have to understand the fundamental architecture of this loop.
Let's visualize this for the listener. Think of a heavily fortified, high-security art museum. The priceless paintings, those are your high-voltage systems. The massive battery packs, the inverters, the spinning electric motor.
Okay, I like this analogy.
Now imagine a meticulously thin, low-voltage security tripwire wrapped around every single access door, every window, every plug, and every control panel in that entire museum.
Right, and this low-voltage tripwire is continuously sending a tiny, completely harmless electrical signal in a closed circuit. The car's computer is just constantly listening to the end of that wire.
Exactly. So if someone jiggles a handle or if a door opens even a fraction of an inch, the tripwire breaks. Signal solid.
And the security system instantly knows the perimeter is compromised without ever having to expose the priceless paintings to actual danger. It just triggers an immediate lockdown.
That is the core mechanism, right? But the true complexity is in how they actually execute it.
Yeah, because this system is designed to meet ASIL D requirements. That is the absolute highest automotive safety integrity level in the industry. It means the tolerance for failure is effectively zero.
Zero room for error.
Exactly. And to unpack how engineers actually achieve the impossible here, we're going to navigate through 5 distinct dimensions of this architecture.
Right. We need to figure out how this tripwire actually breaks in the real world, how the car's digital brain detects that break in milliseconds, and how engineers have basically rewritten the laws of physics and manufacturing to fight back.
It's a massive undertaking.
So let's start with the first dimension, the root cause analysis, the microscopic battlefield. Because before we can build a defense, we really have to understand the enemy. And looking at the sources, the enemy isn't like a massive collision. The enemy is invisible to the naked eye.
Yeah, we have to shift our entire perspective down to the atomic level. The first major mechanism of failure is what they call fretting, corrosion, and oxidation.
I need to push back on this immediately, actually, because the sources paint a picture that seems counterintuitive to me.
How so?
We are talking about heavy-duty, thick copper cables bolted and clipped into these high-voltage junction boxes. How on earth is a bolted connection experiencing movement? Like, where is the physical degradation coming from if everything is locked down tight?
It comes from the fundamental physics of the environment. I mean, a vehicle in motion is not a static object. It's essentially an acoustic and mechanical resonance chamber.
Okay.
The sources specify that these connections are subjected to relentless vibration frequencies, ranging from 100 hertz to 1,000 hertz. That is a continuous, high-frequency mechanical buzz traveling straight through the chassis, into the junction box, and directly into the metal terminals.
So the engine, the road, the tires, they're all conspiring to shake this plug.
Yes, and you couple that mechanical vibration with violent thermal cycling. The power semiconductors driving these hybrid motors, specifically the silicon carbide, MOSFETs, and IGBTs, they generate immense amounts of heat.
Right, because they're switching massive currents on and off thousands of times a second.
Exactly. So the environment inside these completely sealed connectors swings from a freezing negative 40 degrees Celsius in the winter all the way to a blistering positive 150 degrees Celsius under maximum load.
And obviously everything expands when it gets hot and contracts when it gets cold.
Right. And different materials, the copper wire, the plastic housing, the metal bolts, they all have different coefficients of thermal expansion. They grow and shrink at entirely different rates.
So it's constantly shifting.
This constant thermal breathing, combined with that 1,000 hertz vibration, causes the metal pins inside the connector to rub against each other. Engineers call this micro-movement fretting.
And the scale of this fretting is just baffling to me. The documentation measures this movement at 10 to 100 microns.
It's tiny.
A single human hair is about 70 microns thick. We are talking about a microscopic shimmy.
It's imperceptible to us, yeah, but it is devastating to an electrical circuit. Most standard electrical terminals use a tin plating to protect the underlying copper, and tin is a soft metal.
Okay.
As these pins vibrate back and forth across a distance of a single hair's width, they actually begin to scrape that tin plating right off.
I'm picturing like an everyday pencil eraser. If you gently rub an eraser on a desk, just tiny back and forth movements, it eventually wears down into a pile of dry rubber crumbs.
That's a perfect visualization, honestly.
Yeah.
The scraping exposes the fresh, pure tin and copper underneath. And the moment that bare metal hits the air trapped inside the plug, it reacts with oxygen.
It rusts.
It oxidizes almost instantaneously. This creates a microscopic layer of metal oxide, basically the eraser crumbs in your analogy.
But why does a pile of microscopic rust matter to a system pushing hundreds of volts? I mean, shouldn't the power just blast right through it?
Well, because metal oxide is an electrical insulator. When engineers design a metal plug, the entire surface doesn't actually touch. On a microscopic level, metal is rough. It looks like mountain peaks.
Oh, interesting.
The current only actually flows where the highest peaks touch, which are called A spots.
Yeah.
And the metal oxide debris physically wedges itself right between these A spots. It completely blocks the path of the electrons.
So the electrical resistance just suddenly spikes.
Exactly. It jumps from a few microohms, which is essentially zero resistance, way up into the ohms range. This choke point causes that low voltage tripwire signal we talked about to flutter and drop out.
Wow.
We call these micro disconnects, and this is the exact mechanism that triggers the U3529 fault code in the diagnostic system. The tripwire is basically stuttering.
But the high voltage is still trying to get through, right? Which brings us to the second dimension of this root cause analysis, microarcing and carbonization.
Yes, the heavy hitter.
But if we have a pile of oxidized debris acting as a physical roadblock and a massive battery is trying to force current through that roadblock, the physics are going to get violent.
It becomes a literal thermal runaway event at the microscopic scale. The governing principle here is Joule heating. The formula is current squared times resistance.
Okay, math time.
Because the current variable is squared, even a marginal tiny increase in electrical resistance from those oxidized fretting crumbs causes an exponential explosion of heat right at the contact point.
So the metal essentially starts to cook itself.
Exactly. And remember the continuous vibration. As the metal pins continue to fret and vibrate, there will inevitably be a moment where the physical contact breaks entirely, even for just a single microsecond. A physical gap forms.
But electricity, especially high voltage direct current, doesn't just politely stop flowing because a tiny gap appeared, does it?
Absolutely not. The electromotive force, the pressure of the voltage, is just too high. When the contacts separate, the voltage drop across that microscopic air gap becomes so intense that it exceeds the dielectric breakdown strength of the air itself.
Meaning what exactly?
It strips the electrons right from the air molecules, turning the regular air into a highly conductive plasma.
So the air itself basically catches fire and becomes the wire.
A micro-arc. It's a miniature lightning bolt inside the plug. The temperature of that plasma arc can exceed several thousand degrees Celsius in a fraction of an instant.
Good Lord.
It is hot enough to physically melt the heavy copper and tin terminals, turning them into liquid slag.
And the surrounding materials, like the plastic housing and the rubber seals?
They are totally incinerated.
Right.
The intense localized heat hits the polymer insulation and carbonizes it. It burns it into a charred, black mess.
Which ruins the plug entirely.
Yes, once the plastic is carbonized, it structurally fails, forming a permanent, irreversible physical barrier between the contacts. The connection is dead. The tripwire is cut. The high-voltage path is utterly destroyed.
That is insane. So we have thermal expansion and vibration destroying the metals from the inside. But what about the outside? The sources dedicate a massive section to Dimension 3, seal degradation and electrochemical migration, or ECM.
Right, because we have to factor in the operational reality of a car. It's not in a lab. It drives through rain, snow, and salted roads. The engineers utilize heavy-duty floor rubber O-rings to seal these high-voltage connectors and prevent the outside world from getting in.
Rubber is durable, sure, but it's not invincible.
Not at all. Under those extreme thermal shocks we mentioned, the rapid swings from -40 to 150 Celsius, the fluoropolymers in the rubber begin to cross-link and age.
It degrades.
The rubber hardens. It loses its elasticity. Eventually, microscopic microcracks form in the O-ring itself. The mechanical seal is compromised.
And the moment a seal fails on a vehicle undercarriage, it's a disaster. You've got condensation, high-pressure spray from driving through deep puddles, road salt, and sometimes even gearbox oil migrating up the wire harnesses.
It creates a highly corrosive, incredibly toxic soup inside the plug. When water mixed with road salt bridges the microscopic gaps between the metal pins, it acts as a perfect electrolyte.
Okay.
Apply the electrical voltage across that wet, salty bridge, and you trigger electrochemical migration.
I'm struggling to visualize this one. How does electricity interact with salt water to destroy solid metal?
Think of it as a microscopic electroplating factory gone rogue. The electrical field creates an anode and a cathode. The voltage literally forces metal ions to dissolve right off the positive pin into the water, swim across the fluid, and deposit themselves onto the negative pin.
Wait, the electricity is harvesting atoms from one wire and building a physical bridge to the other wire.
Exactly. Yeah. It builds these dendritic structures. They look like tiny, invisible, highly resistive metallic rust trees. They grow completely across the plastic housing until they short out the signal pins.
That's wild.
The pins literally dissolve themselves into sludge. The impedance of the tripwire spikes wildly, and the entire system fails.
It's terrifying how many literal forces of nature are trying to tear this system apart. Which brings me to Dimension 4, and I have to say, reading this in the source documentation completely changed how I look at car manufacturing. They call it the butterfly effect of fasteners.
It is the perfect illustration of how a macro-level oversight on a factory assembly line translates into a microscopic catastrophe out on the highway.
So let's picture the factory floor. You have a worker assembling the main high-voltage junction box. Thick copper bus bars and heavy wire harnesses need to be bolted down super tightly to the metal chassis.
Right.
The documentation explicitly warns about a missing phosphating treatment on the threaded bolts. I don't understand why skipping a chemical dip on a piece of threaded steel could cause a car to lose power at 70 miles an hour.
To understand the failure, you have to understand how modern cars are actually built. A human mechanic isn't standing there with a hand wrench, feeling the tension of every single bolt. They use massive, robotic, pneumatic screwdrivers.
Right, and those tools are programmed to turn the bolt until they hit a specific torque limit, right? It senses resistance, decides the bolt is tight, and stops turning.
And that assumption is exactly the fatal flaw. The robotic tool measures rotational force, which is torque. But what actually holds a heavy copper wire securely against a metal plate is not rotational force at all. It is axial preload.
Axial preload?
Yes, it's the downward physical clamping force of the bolt head.
Okay, so where does the chemical dip come into play here?
A phosphating treatment acts as a microscopic dry lubricant and an anti-corrosion layer right on the threads of the bolt. It ensures that the friction between the turning bolt and the threaded hole is incredibly smooth and uniform.
Got it.
If that chemical treatment is missing, or even just unevenly applied, the raw steel surface of the threads is rough.
So the robotic screwdriver starts driving this untreated rough bolt into the hole?
Yes, and as it turns, it hits a patch of high friction on the raw metal threads. The resistance spikes violently. The machine reads that sudden spike in rotational resistance, assumes it has reached the target torque value, and immediately shuts off.
Wow. So the machine thinks it did a perfect job.
But it didn't. All the rotational energy was totally wasted fighting the friction of the bad threads. The bolt barely clamped down on the copper ring at all. The axial preload is essentially zero.
It's just hanging there.
The physical connection is functionally loose before the car ever even leaves the factory floor.
And then you drive it off the lot.
The 100 to 1,000 hertz acoustic vibrations take over immediately. The alternating mechanical stress works on that under-torqued bolt for months, sometimes years. Eventually, the fastener simply shakes itself free, the heavy cable drops away from the bus bar, and the high-voltage loop physically separates right on the highway.
Skipping a chemical bath on a 30-cent screw cascades into a life-threatening loss of motive power. That is just staggering.
It's the butterfly effect.
So we now thoroughly understand the microscopic battlefield. We know exactly how heat, vibration, chemistry, and friction conspire to break the tripwire. That brings us to the second major part of our journey: technical architecture and software-hardware code diagnostics.
The digital brain of the operation.
Because detecting that the physical connection is dying and detecting it fast enough to actually save the occupants requires an entirely different class of engineering.
It really does. The sources outline a strict ASIL D safety constraint known as the FTTI, the fault-tolerant time interval. And the number they give is chilling, frankly.
Yeah, the absolute maximum allowable FTTI is 60 milliseconds. Less than or equal to 60 milliseconds from the exact moment a fault occurs to the moment the vehicle must be placed into a physically safe state.
Let's contextualize that for a second. 60 milliseconds. A single human eye blink takes roughly 300 to 400 milliseconds.
That's incredibly fast.
If you're startled by a brake light stopping in front of you, your brain takes about 250 milliseconds just to process the visual information and tell your physical foot to move toward the brake pedal.
So the car's diagnostic brain has roughly 1/5 of a human blink to manage a total crisis.
Exactly. In that microscopic sliver of time, the system must detect a tiny voltage drop on the tripwire, verify mathematically that it's a real physical fault and not just an electrical ghost, decide whether to limp the car or shut it down entirely, and mechanically actuate heavy-duty relays to control hundreds of volts of electricity.
It is a terrifyingly fast race against physics. How does a computer even begin to monitor something that fast? The documentation points to active PWM and plausibility checks.
Right. The system cannot afford to just passively sit there and wait for a wire to snap. It has to hunt for degradation actively. The microcontroller injects a high-frequency PWM signal pulse with modulation directly into the low-voltage tripwire loop.
For someone who hasn't stared at an oscilloscope all day, what does a PWM signal actually look like?
Think of it as a perfectly crisp, highly rhythmic heartbeat. It is a square wave, violently switching voltage on and off in incredibly precise, measurable intervals. It sends this complex, high-speed pulse straight down the wire.
And at the end of the loop, another part of the computer is waiting to catch it.
Yes. The main microcontroller utilizes a highly specialized piece of hardware called a GTM comparator, a generic timer module. It samples the returning voltage of that heartbeat pulse in real time, pulling data every few microseconds.
It's just watching it constantly.
It's closely looking at the crisp edges of that square wave. If the fretting corrosion we discussed earlier causes a momentary spike in resistance, the amplitude of that returning pulse drops.
The heartbeat stutters, and the GTM comparator catches the dropping edge instantly.
Exactly. It detects the voltage falling below a pre-programmed threshold and instantly prepares to throw the U3529 fault code.
But hold on, the sources explicitly highlight a massive hurdle here. Modern electric and hybrid vehicles are absolute nightmares of electromagnetic interference. You've got massive magnetic fields spinning inside the motors.
The electrical noise is deafening. We mentioned the silicon carbide power chips earlier. When they switch the high-voltage battery current on and off to generate the AC waves that drive the motors, they do it with terrifying speed.
How fast?
The spec sheets note a DVDTA rate of voltage change over time of up to 10 kilovolts per microsecond.
That is 50 volts every single nanosecond.
It creates a massive electromagnetic shockwave. This violent switching generates severe common mode noise that bleeds into every single wire in the car. To the highly sensitive low-voltage tripwire, this noise looks like chaotic, jagged spikes and deep valleys in the voltage.
So the GTM comparator might see a sudden drop in voltage, assume the wire just snapped, and brutally shut the car down at highway speeds, when in reality, the wire was perfectly intact.
Right, a false positive.
It was just blinded by the electrical noise of the motor switching.
And in functional safety, A false positive at 70 miles an hour is just as lethal as ignoring a real fault. You absolutely cannot have the car randomly slamming its own emergency brakes because of electrical static.
So how does the car differentiate between a dying wire and electromagnetic static?
This is where the sheer brilliance of the plausibility algorithm comes into play. The software architecture refuses to look at the tripwire voltage in isolation. It mandates a continuous, highly complex dynamic cross-verification.
It double-checks its math.
Precisely. It constantly compares the raw, high-voltage DC bus data, the actual power flowing to the motors, against the low-voltage equivalent residual signals coming off the tripwire. It is constantly calculating the impedance consistency across multiple domains.
That sounds like incredibly heavy computational math. Break down how that actually filters the noise for us.
Okay, think of noise-canceling headphones. If you are on an airplane, the headphones listen to the low, chaotic roar of the jet engines, invert that exact sound wave mathematically, and play it back into your ears to cancel the noise out.
Leaving only the pure sound of your music.
Right. The plausibility algorithm does something very similar, but digitally. It analyzes the high-frequency jitter of the voltage. By looking at the mathematical pattern of the flutter, the algorithm can perfectly distinguish the random, disorganized static of the silicon carbide chips from the highly specific stuttering resistance curve of a corroded physical connection.
It mathematically subtracts the roar of the engine so it can listen to the whisper of the dying tripwire. It filters out the ghosts.
Exactly. It ensures the alarm is only ever triggered when the physical metallurgy of the connection actually degrades.
Okay, so the plausibility algorithm has done its math. It has verified through all the static that the wire is genuinely failing. The clock is ticking down from 60 milliseconds. Who actually makes the final call to execute the safety protocol?
This brings us to the physical architecture of the silicon itself, the doer-checker dual-core system.
This detail feels like it was ripped straight out of a commercial aviation flight manual.
The level of redundancy is truly aerospace grade. The central processing unit isn't just one brain. It is completely divided. You have the main microprocessor core designated as the doer. Its entire existence is dedicated to running the complex field-oriented control algorithms to spin the motors, manage the lithium-ion cell balancing, and translate the driver's throttle pedal into physical acceleration.
The doer is the pilot flying the plane. It has a lot on its plate.
It is entirely consumed by the task of driving. But physically printed on the exact same piece of silicon, right next to the doer, is a secondary, physically independent microprocessor core. This is the checker.
The co-pilot.
And the checker core has absolutely no interest in driving the car. It doesn't care about your climate control, your radio, or how fast you want to accelerate. Its solitary, unwavering purpose is to monitor the high-voltage safety chain.
So you have a pilot flying the plane and a co-pilot whose only job is to just stare out the side window at the wing to make sure it hasn't caught fire.
And they operate in a strict state called lockstep. The checker is continuously comparing its safety calculations against the state of the doer. But here's the critical failsafe. If the checker core receives the verified flag from the plausibility algorithm that an HVIL fault has occurred, it does not politely ask the doer core for permission to shut down.
It doesn't consult the pilot at all.
Not at all. It completely bypasses the main operating system. The checker core utilizes hardware-level interrupts. It forcefully seizes control of the power electronics within 100 microseconds of the fault verification.
Wow.
It bypasses the software entirely to ensure the safety intervention begins immediately, keeping the total reaction time well under that 60 millisecond threshold.
The co-pilot has their own dedicated emergency brake, and they pull it without asking. But that leads to a massive physical problem. The sources are incredibly explicit about this. You cannot simply cut the power cord on a vehicle traveling at highway speeds.
Absolutely not. Yanking the main battery contactors open while the vehicle is at speed would be a catastrophic event. The system must intelligently choose between two distinct interventions based on the physics of the moment: adaptive limp-home mode or a hard cutoff.
Let's start with limp-home. If the co-pilot sees the tripwire degrading, why not just instantly shut down the motors and let the car naturally roll to a stop?
Because of the fundamental physics of electromagnetism, an electric motor and an electric generator are physically the exact same machine, just operating in reverse.
Explain that mechanism. How does turning off a motor suddenly turn it into a generator?
Well, when you're driving, the battery pushes electrical current into the copper windings of the motor, creating a rotating magnetic field that chases the magnets on the rotor, spinning the wheels.
Makes sense.
But if you blindly command a safe torque off a hard shutdown, you suddenly cut that incoming current. But the physical rotor, which is attached to the wheels of the car, is still spinning furiously at thousands of RPMs because of the forward momentum of the heavy vehicle.
Right, the car is still moving forward at 70 miles an hour.
Exactly. So those spinning magnets on the rotor are now passing rapidly over the dead copper windings. According to Faraday's law of induction, a moving magnetic field passing over a conductor naturally induces an electrical current in that conductor. The motor instantly becomes an uncontrolled, high-voltage generator.
Pumping massive amounts of electricity backward into the system.
This phenomenon is called EMF back electromotive force. This sudden, violent surge of uncontrolled, high-voltage energy rushes backward into the power electronics. It can easily exceed the voltage rating of the silicon carbide power tubes and literally blow them apart.
That sounds expensive and dangerous.
It is. Alternatively, the sudden, unmanaged loss of driven torque can cause a massive deceleration shock, instantly locking the drive wheels and throwing the vehicle into an uncontrollable 70-mile-an-hour spin.
So a hard shutdown either blows up the computers or crashes the car. Neither is an acceptable outcome.
Which is why, if the vehicle is in motion and detects a tripwire fault that isn't an immediate dead short circuit, the checker core initiates an over-the-air or OTA adaptive limp-home strategy. It executes a highly managed mathematical retreat.
How does it manage that retreat without triggering the back EMF?
It doesn't just turn the power off. It actively restricts it mathematically. The software mandates a precise descent slope of 500 newton meters per second. It commands the inverters to gently but firmly ramp down the magnetic fields.
Slowly bleeding the power.
Yes. It restricts the maximum torque output to just 30% of the nominal rating, and it electronically governs the vehicle's top speed to 40 kilometers per hour.
It forces the car into a slow, highly controlled crawl rather than a brutal shutdown.
It bleeds the energy out of the system safely. And crucially, the specification dictates that this limp-home mode must provide the driver with enough continuous power to achieve a 100-mile safety buffer.
That detail is profound to me. The engineers prioritized predictable human safety. They completely refused to design a system that panics, shuts off the machine to protect its own circuitry, and strands a family in the fast lane of a busy highway. They designed a system that actively manages its own failure state to gently walk you to the shoulder of the road.
It is the absolute essence of functional safety. However, there's a second scenario. What if the tripwire isn't just degrading due to fretting over time? What if the fault is triggered by a massive, catastrophic physical collision? What if the airbags deploy while the vehicle is traveling over 80 kilometers per hour?
In a high-speed crash, the chassis is crushing inward. You have to sever the high voltage immediately to prevent raw electricity from pumping into the crushed metal frame and electrocuting the passengers or the first responders. You can't limp home from a wrecked car.
Exactly. This scenario absolutely demands a hard cutoff. But we still have that back EMF problem we just talked about. The wheels are still spinning, the motor is generating lethal voltage, and you cannot simply pop the main mechanical battery relays open.
Why not? Just sever the physical connection to the battery.
Because if you open a physical switch while thousands of amps of current are actively flowing, the electricity will just arc across the opening gap. It will weld the relay contacts completely together or violently blow the relay housing apart. The energy has nowhere to go.
Yeah.
You must stop the motor from generating voltage instantly without blowing up the relays.
How is that even physically possible?
The engineers execute a breathtakingly violent two-stage maneuver called stepwise active short circuit, stepwise ASC.
Wait, they deliberately short-circuit their own motor. I'm sorry, I don't understand that. Isn't short-circuiting a massive electrical system exactly how you cause a fire?
In a normal circuit, yes, absolutely. But here, they use the heavy-duty power electronics to intentionally connect the motor's own phase wires directly to each other. By shorting the motor phases together, you instantly drop the voltage differential across the motor to zero. The motor can no longer push voltage back toward the battery.
So where does all that rotational energy go?
It gets trapped inside the heavy copper windings of the motor itself, where it just harmlessly dissipates as thermal heat. But they have to do it in very specific steps.
Why in steps? Why not just short all 3 wires at once and be done with it?
Because if you short all 3 phases of a massive electric motor instantaneously at 80 kilometers per hour, the sudden, violent magnetic braking torque generated would be so immense that it could physically snap the hardened steel axles right in half or violently tear the heavy motor mounts straight out of the chassis.
The mechanical shock would literally tear the car apart.
Exactly. So stage 1. The computer triggers a 2-phase short circuit, or 2 PSC. It only shorts 2 of the 3 heavy wires together.
What does that accomplish?
It acts as a microscopic pressure release valve. It holds this two-phase short for exactly 1.5 milliseconds. This tiny window is just enough time to bleed off the sharpest, most dangerous initial spike of magnetic energy, what they call the demagnetization current peak.
It shaves the violent edge off the shockwave.
Then, stage 2. The exact instant that 1.5 millisecond peak has passed, the system triggers the 3-phase short circuit, fully locking down the electromagnetic generation of the motor. This stepwise maneuver successfully clamps the wildly surging direct current bus voltage safely below 720 volts.
720 volts, which is well within the safe operational limits of the insulation and the relays.
Precisely. Once the checker core verifies that the voltage is safely clamped and stabilized below that 720 volt threshold, only then does it actively command the massive mechanical contactors on the battery pack to physically spring open.
Brilliant.
It safely severs the main power supply from the crushed vehicle without any risk of secondary arcing or welding.
It is an orchestrated ballet of electromagnetic destruction executed flawlessly in milliseconds just to save human lives. It is absolutely phenomenal. Okay, so we have deeply explored the digital brain. We understand how it detects the fault and manages the crisis. But managing a failure is always secondary to preventing the failure in the first place. Which leads us to part 3. DFMEA, Key Design Prevention Controls, the blueprint defense.
Right. The engineers analyzed the microscopic battlefield we detailed in part 1. They saw the fretting, the thermal expansion, the arcing, and the electrochemical migration. And they went back to the drawing board to radically redesign the physical hardware of the plugs themselves.
And looking at the specs, they started at the foundational atomic level with material upgrades. The source document dictates a massive, uncompromising shift in the metallurgy of the connectors. The first absolute rule: brass is permanently banned.
No more brass in high-voltage critical systems. Ever.
Why ban brass? I mean, it's cheap, it's highly conductive, it's been used in electrical work for decades.
Brass has terrible mechanical fatigue strength, especially at high temperatures. In an environment that is vibrating at 1,000 hertz and baking at 150 degrees Celsius, a brass spring clip simply gives up. The heat anneals the metal, relaxing its crystalline structure.
It gets soft.
Yes, it loses its springiness and it stops gripping the mating pins securely.
And the moment it stops gripping tightly, the thermal fretting vibrations begin all over again. So what alloy do they replace it with?
The engineering specification firmly mandates the use of phosphor bronze. Phosphor bronze is an incredibly resilient copper alloy. Even under extreme thermal loads and violent vibration, it maintains an exceptionally high yield strength. It acts like a stiff, relentless, completely unyielding spring.
Wow.
The design specifically dictates that the connector mechanism must maintain a constant normal force of greater than or equal to 1.5 newtons pressing against the pin at all times.
So it physically hugs the pins so aggressively that those 10 to 100 micron fretting movements literally cannot occur. The two pieces of metal are fused together by pure mechanical clamping force.
Exactly. They eliminate the mechanical root cause, but they didn't stop at the base metal substrate. They fundamentally changed the surface plating too. We discussed how tin plating scrapes off and oxidizes into an insulating rust. The new specification demands a gold over nickel dual layer plating.
Now, using gold makes obvious sense to me. Gold is highly conductive, and it is a noble metal, meaning it doesn't react with oxygen. It doesn't rust or tarnish. But why mandate a layer of nickel underneath the gold? Why not just plate the gold directly onto the phosphor bronze base?
That requirement solves a fascinating, almost invisible problem in material science. If you plate pure gold directly onto a copper-based alloy like phosphor bronze, over time, and especially when exposed to the 150 degrees Celsius operating temperatures, the copper atoms possess enough thermal energy to literally migrate up right through the crystalline lattice structure of the gold layer.
Wait, the copper atoms physically bleed straight through solid gold?
Yes, it is called solid-state diffusion. The copper atoms basically push their way to the surface, and once that copper breaches the surface of the gold, it reacts with the oxygen in the air, oxidizes, and builds that exact same insulating barrier of debris we were trying to avoid. You've completely wasted the huge expense of the gold plating.
So the nickel layer stops that process.
The nickel acts as a vital, impenetrable metallurgical barrier layer. Its atomic structure completely prevents the copper from migrating upward, It stands between the base copper and the surface gold, stopping the atomic diffusion cold.
I love that visual. It's a metallurgical bouncer standing at the door, physically keeping the unruly copper atoms out of the VIP gold lounge.
That is an incredibly accurate way to describe it. And the specification demands that the final gold layer must be exceptionally robust, greater than or equal to 1.27 microns thick. This substantial thickness ensures long-term physical survival against any residual insertion friction during the factory assembly.
Okay, so they perfected the materials, but then we move to the physical geometry of the wiring. And this is where we talk about the drip loop. After all the complex metallurgy and dual-core processors, this concept is beautifully, almost comically simple.
It really is the hallmark of elegant mechanical engineering. We detailed earlier how water, condensation, and road salt creep down the wiring harnesses and destroy the sensitive seals, causing electrochemical migration.
Right, and you counter that massive chemical threat with literally a bend in the wire.
A simple, deliberate, U-shaped bend. The strict mechanical specification mandates that before any high voltage or signal cable is allowed to enter the motor housing or junction box, it must have a minimum 50-millimeter drop.
It forces the wiring harness to dip down toward the road into a U-shape before coming back up to plug into the water-type box.
Yes, because while seals naturally degrade and polymers crack over time, gravity is flawlessly reliable. Any water, condensation, or corrosive salt spray that lands anywhere on that wire will naturally run down the insulation to the lowest point of that U-shape, where it will harmlessly drip right off onto the pavement.
Incredible.
Water physically cannot defy gravity to climb back up the other side of the wire to penetrate the connector housing.
It's mechanical moat, defeating complex chemistry with simple gravity. It's brilliant. Now, let's contrast that simple exterior bend in the wire with the extreme geometrical complexity hidden inside the plug itself. Hyperboloid basket contacts.
Ah, yes, the hyperboloid contacts. If you pull apart a standard, cheap electrical connector, you usually find a simple solid metal pin sliding into a split metal tube. At a microscopic level, they might only actually touch at 2 or maybe 3 distinct points.
Which means if a violent pothole vibration momentarily jars those specific 2 points apart, the signal drops completely.
Exactly. A hyperboloid contact design throws out the simple tube entirely. It replaces the female receptacle with a woven, complex mathematical basket of highly tensioned spring wires. Imagine a Chinese finger trap constructed entirely from phosphor bronze.
Oh, that's a great image.
When the male pin slides into this basket, the wires twist and stretch, gripping the pin securely from 360 degrees.
So how many contact points does that actually create?
It provides between 10 to 20 independent parallel connection points all along the length of the pin.
So even if a violent vibration momentarily breaks the physical contact on 1 or 2 of those microscopic wires, you still have 18 other independent, redundant paths for the electricity to flow flawlessly.
It introduces massive physical redundancy right at the millimeter scale. The geometry almost entirely mathematically eliminates the risk of a single-point micro-disconnect.
It's just an armor-plated design. Okay, let's look at the final layer of defense in Part 3. Chemical and electronic defenses. Because they add one more invisible shield to the plug, don't they?
Right. The manufacturing blueprint requires the automated injection of a highly specific chemical compound directly into the internal housing of the plug, Niogel 760G.
The sources describe it as a fluorosilicone grease. Now, my immediate thought is, grease is an insulator. Doesn't pumping grease into an electrical plug block the flow of electricity?
Niogel is a dielectric material, meaning, yes, it is an electrical insulator, but remember the immense normal force of those phosphor bronze hyperboloid springs. They are clamping down on the pin with over 1.5 newtons of force.
Right.
That mechanical pressure is easily strong enough to physically slice right through the microscopic 10-micron layer of grease at the exact points where the metals actually need to touch.
So the metal-to-metal connection just pushes the grease out of the way, allowing electricity to flow perfectly at the contact points. But what about the rest of the grease packed inside the housing?
The grease flows into and completely fills every single remaining microscopic void and crevice inside the plug housing. It aggressively displaces all the ambient air.
And without air, there is no atmospheric oxygen. Without oxygen, there is no oxidation. No insulating rust crumbs can form.
Exactly. The Niogel creates a perfect, impenetrable chemical encapsulation of the connection, permanently sealing it against atmospheric humidity and oxygen. And lastly, we must look at how they upgrade the electronic components on the circuit board itself to fight that massive silicon carbide switching noise we discussed earlier.
Right, the 10 kilovolt per microsecond electromagnetic shock waves. The hardware needs to help out the plausibility algorithm.
They do this by mandating the use of Class 1 C0G, also known as NP0, ceramic capacitors in the low-voltage filter circuits. These specific capacitors are highly engineered to be incredibly stable. Their capacitance values do not drift or change wildly when subjected to the extreme temperature swings inside the inverter.
Okay.
And they pair these stable capacitors with ultra-precision resistors rated with a manufacturing tolerance of plus or minus 0.1%.
Why go to the massive expense of demanding components with such extreme precision?
It is to achieve perfect differential symmetry. In this architecture, the sensitive signal don't travel down a single wire. They travel down a pair of tightly twisted wires. The computer sends the exact same signal down both wires, but it mathematically flips one of the signals completely upside down, a phase inversion.
So one wire carries a positive wave and the other carries the exact same wave, just negative.
Correct. Now, when that massive electromagnetic noise from the motor blasts through the chassis, it hits both of those tightly twisted wires equally, adding the exact same noise spike to both signals simultaneously.
But because the original signals are mirror images.
When those two signals reach the microprocessor, the computer subtracts one wire from the other. Because the noise spikes on both wires are identical and in the exact same direction, subtracting them perfectly cancels the noise out to absolute zero.
Wow.
It's mathematically erased. This is called the common mode rejection ratio. But this mathematical magic only works if the physical filter circuits on both wires are perfectly identically matched.
Which is exactly why you need the ultra-precision 0.1% resistors and the stable COG capacitors. If one resistor was even slightly different due to heat, the noise wouldn't cancel perfectly, and the static would bleed straight through to the computer.
Precisely. By forcing the hardware to be perfectly symmetric, the noise is mathematically destroyed before it ever reaches the microprocessor's delicate logic gates.
This blueprint is a technological fortress. I mean, they have systematically attacked the root causes of failure using metallurgy, geometric redundancy, chemical encapsulation, and mathematical phase inversion. But as we transition to part 4, we have to face the harsh reality of mass production. A perfect blueprint means absolutely nothing if the exhausted human being on the assembly line is having a bad day and makes a mistake.
Which is the fundamental, terrifying challenge of scaling any complex engineering to mass production.
And that brings us to the PFMEA key process controls, the factory floor fortifications. How on earth does an automaker guarantee these microscopic 10-micron tolerances when they are stamping out hundreds of thousands of cars a year?
They rely on an obsessive manufacturing philosophy called pope-yoke.
Mistake proofing.
Exactly. It is the practice of designing the manufacturing process so that human error is physically impossible to make. For example, the specification explicitly and permanently bans any manual wire stripping on the high-voltage lines. A human worker, using a hand tool or a razor blade, no matter how incredibly skilled they are, might accidentally nick or score one single microscopic strand of copper in a thick wire bundle.
And if you nick a strand, it breaks. That means less copper to carry the massive current. That one broken strand becomes a high-resistance choke point that slowly overheats and burns the car to the ground 3 years later.
Exactly. So all wire stripping is executed by precision, laser-guided automated machinery, and when it comes to the highly critical step of crimping the metal terminal onto that stripped wire, they do not rely on a worker pulling a handle. They use automated hydraulic 360-degree crimping presses. But the machine doesn't just blindly crush the metal together.
This is where the process control gets highly analytical. The sources detail the use of closed-loop force displacement curve monitoring during the crimp.
This is a beautiful piece of real-time quality control based on Hooke's law and material deformation. As the hydraulic press squeezes the metal terminal onto the copper wire strands, high-resolution sensors measure exactly how much force is being applied millisecond by millisecond.
Okay.
They plot that exact force against exactly how many millimeters the metal has physically deformed.
It basically generates a highly detailed curve on a graph representing the physics of the crush.
Yes. And the computer controlling the press knows exactly what the mathematical signature of a perfect, solid copper crimp looks like. If a single tiny strand of wire is missing from the bundle, or if a tiny piece of dirt got into the terminal, or if the metal is too hard, the physical resistance will change.
Makes sense.
The force displacement curve will suddenly deviate from the perfect master signature.
The machine literally feels the physical anomaly inside the metal as it crushes it.
Instantly, the
Got it.
machine flashes a red warning light. But more importantly, the pokey yoke mechanism, the machine, physically locks the defective wire harness inside the heavy metal clamping jig.
Wait, it traps it? The human operator literally cannot pull the bad part out and quietly pass it down the line to hit their daily quota.
Correct. The machine unequivocally refuses to release the part. A quality control supervisor has to physically walk over, inspect the failure data, use a special key to unlock the machine, and personally throw the defective harness into a locked scrap bin. You aren't just inspecting the final product at the end of the day, you are mathematically monitoring the molecular physics of the creation of the product in real time.
That is mistake-proofing at its absolute finest. Now, what about that Niogel fluorosilicone grease we talked about earlier? We established how vital it is for blocking oxygen and preventing rust. How does the factory guarantee that a robotic nozzle pumped exactly the right amount of grease deep inside every single tiny plug housing? You can't even see inside it once it's closed.
They use a brilliant visual chemistry trick. Before the bulk grease is ever loaded into the automated microdispenser on the factory floor, the supplier mixes a highly specific UV fluorescent tracer dye directly into the chemical compound.
They basically turn it into invisible ink.
Exactly. The robotic needle injects the grease deep into the blind cavity of the plug. Then the part moves down a conveyor belt under an AOI station, an automated optical inspection array. High-resolution industrial cameras look straight down into the plug cavities, and high-intensity strobes blast the part with ultraviolet light.
And the invisible grease suddenly glows.
It glows intensely bright green or blue. The machine vision software analyzes the pixel density of that specific glow. It mathematically verifies that the chemical coverage is exactly 100%. It checks for dry spots where air could reach the metal, and it checks for overspillage that might contaminate other components.
That's incredibly thorough.
Only when the software calculates a perfect, unbroken fluorescent geometric ring does it unlock the pallet and let the part move to the next assembly station.
The layers of automated verification are staggering to me. And it all culminates at the very end of the line, the EOL testing.
This is the final exam. They take the entire, fully assembled power control system, plug it into a test bench, and run a high-speed dynamic impedance test. They fire complex, high-frequency electrical pulses entirely through the completely assembled HVIL tripwire loop.
And the tolerance for failure is razor thin. The specification states they outright reject any system with an internal impedance greater than 5 milliohms.
0.005 of a single ohm. It demands an electrically perfect connection. They simultaneously test the equipotential bonding straps. Those are the thick, braided, bare metal ground wires that connect the aluminum computer boxes directly to the steel chassis of the car. The spec demands those straps measure less than 10 millions of electrical resistance.
I assume that is to make sure all that high-frequency 10 kilovolt electromagnetic noise has a massive, safe, ultra-low resistance pathway to dump right into the ground of the chassis, keeping the static far away from our sensitive tripwire.
Precisely. It entirely guarantees the integrity of the shielding. But the final and perhaps most crucial factory check isn't physical or electrical at all. It is purely digital. Cybersecurity.
Yes, the source documentation explicitly details the use of a SHA-256 hash checksum before the part can be boxed up. Now, I know SHA-256. It is the cryptographic hashing algorithm used to secure things like Bitcoin and high-level banking data. Why on earth is an automotive factory using high-level NSA-grade cryptography on a motor controller?
Because of the staggering software complexity we discussed in Part 2. Think about the massive architecture. You have the doer core running the motor, the checker core monitoring safety, the battery management software, and the plausibility algorithms all working together.
All these independent modules constantly interacting and sharing data at microsecond speeds.
Now, imagine a very common scenario on a chaotic factory floor, or even later when the car goes to a dealership for routine service. A technician flashes a software update, but one module successfully gets the new version, while another module accidentally retains the old version. Or a memory chip gets a tiny single-bit corruption during the flashing process.
The software versions are mismatched or slightly damaged.
And if those deeply intertwined software matrices mismatch even slightly, the complex safety algorithms might totally misinterpret a perfectly normal sensor reading. The checker core might panic, throw a fake U3529 fault code, and violently trigger the stepwise active short-circuit shutdown while you are driving perfectly safely down the road.
A simple software glitch braking the car at 70 miles an hour.
Exactly. So on the factory floor, before that computer is legally allowed to leave the building, the Central Manufacturing Execution System, the MES, reads every single line of code flashed onto every single chip. It runs that entire massive data set through the SHA-256 algorithm to calculate a cryptographic hash.
It crunches millions of lines of code into one single, highly unique digital fingerprint.
And due to the avalanche effect of cryptographic hashing, if even a single 1 or 0 out of millions is out of place, the resulting fingerprint completely changes. The MES compares the fingerprint of the unit on the line against the master mathematically perfect engineering blueprint. If those hashes do not match perfectly, the factory system unequivocally refuses to print a tracking barcode for that part. It physically cannot be sold or installed in a vehicle.
It is genuinely fascinating how holistic this functional safety philosophy actually is. We have transitioned from the tangible physical reality of measuring a millim of electrical resistance all the way to the abstract digital reality of SHA-256 cryptography. The physical hardware and the digital software are completely, inextricably intertwined.
Which means the ultimate validation testing must be equally brutally intertwined. Which brings us to our final destination in this engineering journey, Part 5, DVP&R production validation.
The torture chamber.
Exactly. The product has been theoretically designed to perfection and assembled with absolutely zero acceptable defects. Now, the validation engineers take over, and their entire job is to try their absolute hardest to completely destroy the product. They must empirically prove it is worthy of being installed in your driveway.
Let's walk through this sequence of horrors because it is intense. First up, vibration and thermal hell.
The testing standards dictated here are frankly abusive. They take the entire heavy power control system and bolt it rigidly onto a massive 3-axis electrodynamic shaker table. And they program that table to violently shake the system with a random chaotic force of 35 meters per second squared RMS.
That is almost 4 times the force of gravity, thrashing in every direction simultaneously.
Continuously, without stopping. For 1,000 hours, that is over 40 solid days of relentless high-G mechanical assault. And while it's being shaken to death, the entire table is sealed inside an environmental chamber that blasts the unit with rapid thermal shocks, plunging the temperature to negative 40 degrees Celsius, holding it there, and then rapidly baking it up to positive 125 degrees Celsius.
They are mathematically compressing a 15-year lifetime of freezing winter potholes and blazing summer highway driving into a month and a half of concentrated, unending torture.
And while all this physical and thermal violence is happening, they have highly sensitive oscilloscopes actively monitoring the continuous low-voltage tripwire. The absolute passing criteria to graduate this test. After 1,000 hours of torture, the electrical contact resistance of those hyperboloid pins cannot increase by more than 1.2 milliohms.
1.2 thousandths of an ohm. Barely a whisper of measurable degradation after 40 days of shaking.
And critically, during the entire duration of the test, the logging equipment must record absolutely 0 microdisconnects longer than a single microsecond.
Not a single tiny drop in the heartbeat.
And when the 1,000 hours are finally over and the unit is pulled from the chamber, the engineers don't just look at the data and say, okay, it passed, let's ship it. They perform DPA destructive physical analysis.
They cut the plug completely open.
They take the connector that survived the test, cast it in solid epoxy resin, and use precision diamond saws or lasers to slice it directly in half. They polish the cross-section and put it right under a scanning electron microscope.
To look for what?
They physically visually verify that the 1.27 microns of gold plating didn't wear through to the nickel barrier, and that the phosphor-bronze substrate didn't suffer any microscopic friction oxidation or stress fracture.
Oh, they demand absolute, undeniable visual proof of physical survival. Okay, so the metallurgy holds up. What about the environmental torture? The water, the salt, the seals.
We established earlier that water and road salt act as the perfect electrolyte for electrochemical migration. So they place the sealed units in a specialized corrosion chamber for 96 solid hours of continuous dense salt fog spray. They follow that up with 100 grueling cycles of intense heat and 95% condensing humidity.
They are aggressively trying to force moisture past the age of fluororubber O-rings and defeat that drip loop.
Once it survives the humidity, they pull out the industrial pressure washers. This is the IP67 and IP69K testing protocol. They blast the seals from every conceivable angle with high-pressure scalding hot water jets at very close range.
Literally trying to physically blast the rubber seals right out of their grooves. And after all that aquatic abuse, how do they actually know the inside is dry?
They perform the Mager test, They connect specialized testing equipment and apply a massive, continuous 500-volt DC charge entirely across the plastic insulation and the seals.
The voltage acts like a searchlight. It's actively trying to force electricity to leak through any microscopic drops of water that might have somehow made it inside the housing. If water got in, the electricity will follow the water trail and jump the gap.
Exactly. And to pass, the measured insulation resistance must remain greater than or equal to 100 megaohms. It must remain perfectly uncompromisingly sealed. No rust, no internal arcing, absolutely zero electrical leakage.
Unbelievable. Okay, so the physical box survives the shaking, the baking, the salt, and the flooding. But what about the digital brain inside? How do they validate that 60 millisecond FTTI reaction time, the plausibility algorithm, and the doer-checker lockstep we talked about? You obviously can't test that safely by actually crashing a real car on a test track thousands of times.
No, the real-world variables are way too dangerous and too uncontrolled. To test the software logic, they construct the ultimate synthetic test environment, the FPGA Hill matrix, hardware in the loop.
Explain the architecture of this setup. It sounds entirely like the premise of the movie The Matrix.
The analogy is perfectly accurate, honestly. They take the actual physical printed circuit board of the car's computer, the silicon brains containing the doer and checker cores, and they plug it directly into a massive, floor-to-ceiling supercomputer server rack. This supercomputer is powered by FPGA's field programmable gate arrays. These are specialized chips that can calculate complex physics simulations in nanosecond real time.
So the car's computer is physically sitting in a quiet lab, but its sensors are plugged into a supercomputer that is constantly lying to it. The car's brain fully believes it is driving a heavy vehicle down a real road.
Precisely. The supercomputer feeds the car's processor highly realistic dynamic simulated sensor data. The engineers use the supercomputer to spin the virtual electric motors up to a screaming 12,000 RPMs under full, heavy regenerative braking loads. The car's brain is working furiously, actively managing massive simulated currents and calculating complex torque vectoring.
The processor is maxed out, fully task-loaded, flying the simulated plane, and then the engineers pull the rug out.
While the virtual motor is screaming at 12,000 RPMs, the test engineers forcefully inject a digital fault. They trigger an ultra-fast electronic switch that opens the simulated HVIL tripwire circuit for precisely 1 single microsecond. And simultaneously, they command the supercomputer to blast the sensor lines with extreme chaotic electromagnetic interference noise, attempting to completely overwhelm and confuse the plausibility algorithm.
It is the ultimate chaotic stress test of the digital architecture. They are throwing absolutely everything at the co-pilot at once.
And the system must perform flawlessly. The plausibility algorithm must successfully mathematically cut through the injected noise, accurately recognize the 1 microsecond voltage drop as a genuine fault, and alert the checker core. The checker core must then violently interrupt the doer core and trigger the safety protocol, all in under that strict 60 millisecond window.
It has to initiate the managed retreat while under heavy fire.
It must smoothly command the virtual inverters to transition into limp-home mode, safely dropping the immense 12,000 RPM torque down to 30% without inducing any sudden jarring mechanical jerks over 5 Newton meters. Or, if the engineers simulate a high-speed crash scenario, the system must perfectly, instantly execute the stepwise active short-circuit maneuver.
It has to short the virtual motor phases to clamp the wildly surging virtual DC bus below 720 volts before safely commanding the virtual relays to open.
It is testing the absolute razor-edged limits of modern software and hardware engineering in a completely safe, repeatable environment. And a fascinating note from the engineering sources. Long before they even build these physical HVIL supercomputer rigs, the engineers use advanced Python-based software simulation tools.
They simulate the computer before they build the computer that simulates the car.
Exactly. They mathematically model the high-frequency common mode noise and the complex impedance decoupling of the circuits. They do this to calculate the exact, perfect parameters for their EMC filters, the precise values for those Class 1 COG capacitors and 0.1% resistors we discussed.
They ensure the physical hardware is mathematically optimized to survive the chaos of the matrix before the soldering iron ever touches the circuit board.
It is a profound iterative loop of virtual design, mathematical optimization, and brutal physical validation.
Okay, let's take a collective deep breath, because we have traversed an immense landscape of engineering today. We started by zooming in on a microscopic 10-micron gap in a piece of vibrating metal, a gap the width of a human hair.
The fretting corrosion, the microscopic genesis of a completely catastrophic failure.
And from that tiny invisible gap, we traced the electrical firestorm of plasma microarcing. We watched as engineers countered that severe thermal threat with aerospace-grade, dual-core, lockstep microprocessors, making life-or-death mathematical calculations in fractions of a millisecond. We saw them literally reinvent the metallurgy of the connection with phosphor-bronze and solid-state diffusion blocking nickel layers, while simultaneously relying on the elegant, simple gravity of a U-shaped drip loop.
We walked the chaotic factory floor, where ultra-precise force displacement curves and glowing UV fluorescent grease eliminate the terrifying variable of human error.
And finally, we watched the entire holistic system survive a 12,000 RPM virtual supercomputer torture test while being physically shaken, frozen, boiled, and blasted with high-pressure washers. Exploring this specification completely, utterly redefines what a simple plug is. It is not just a cheap piece of molded plastic and stamped metal. It is a highly engineered, mathematically optimized, actively monitored fortress.
It truly is a marvel of human ingenuity. And for you listening, I think the major takeaway here is to cultivate a profound appreciation for the invisible, silent shields built right around us. The next time you step on the accelerator pedal in a modern hybrid or electric vehicle, and you feel that smooth, silent, effortless rush of power, take a fraction of a second to think about the thousands of microsecond mathematical calculations happening in the silicon beneath you.
Yeah.
Think about the brilliant mechanical fail-safes, the intricate metallurgical barriers, and the relentless torture testing working flawlessly silently in the background solely to keep you safe.
It gives you a whole new level of respect for the machine and the minds that built it. Yep. But as we wrap up this deep dive, I want to leave you with a final thought to mull over. Something that builds on absolutely everything we've unpacked today. We spent the last hour looking at the absolute bleeding edge of ASIL D functional safety standards for a modern electric car rolling down a flat highway. But look at where global technology is aggressively heading. We are rapidly moving into an era of massive artificial intelligence data centers that consume gigawatts of raw power. And more relevantly, we are looking straight down the barrel of commercial electric aviation heavy passenger drones and flying electric taxis.
Systems that will draw vastly more high-voltage power, experience vastly more severe 3D acoustic vibrations, and face infinitely more extreme thermal and environmental conditions than a passenger car.
Exactly. The physics change entirely.
Okay.
If a highly engineered tripwire fails on a highway in your car, the system executes a managed retreat and you limp safely to the shoulder. If a tripwire fails at 5,000 feet in a flying electric taxi well, gravity is no longer your fail-safe friend pulling water down a drip loop. Gravity is instantly your most lethal enemy.
The stakes transition entirely from managing a roadside inconvenience to preventing a catastrophic fall from the sky. The margin for error vanishes completely.
So the question I leave you with is this. As these electrified systems scale up in sheer power and vertical altitude, how will these microscopic battles against thermal expansion, friction, heat, and electromagnetic noise evolve? Will our current gold standard ASIL D architectures, our phosphor-bronze alloys, and our 60-millisecond lockstep reaction times be remotely enough? Or are engineers going to have to discover entirely new realms of physics, material science, and quantum computing just to keep those future high-altitude tripwires intact? It is a staggering engineering challenge to think about.
The diagnostic muddy waters we navigated today are only going to get deeper, darker, and vastly more complex.
Indeed they are. Thank you all so much for joining us on this incredibly intricate deep dive. We'll catch you on the next one.